Hi everyone, this is question number 31 in chapter 2. We have to solve the following problems related to the rates of change. So the rate of change is always differentiate with respect to the time, d by dt. Okay, so let's look at part A. So a cube has sides of x cm, and if the volume, okay, the information that we have is the volume increases at this rate. So let's write down, we have dv by dt. So the rate of change in terms of volume is 2 cm cubic per second. We have to find the rate of change of the side. So the rate of change of the side, so let's the side, since the side is xcm, so we're going to find dx by dt. This is the one that we need to find at the instant when v equals to 729. All right, now we have a cube. So let's just draw the cube. Okay, optional. All right, I just have the habit to sketch the diagram. Okay, so we need to find dx by dt. So we use the chain rule. So we separate the dx and dt and we chain together with dv. Okay, why dv? Because I have dv by dt. So we shall chain that together. All right, so this one we have, but this one we don't have, right? Never mind. We form the equation that relate the v and the x. That is, volume of the cube is actually x cubed. Therefore, if we differentiate v with respect of x, we will have 3x squared. And then at the instant v equals to 729, and we know that v equals to 729, therefore x cubed equals to 729. So we can find the value of x. So the value of x will be cube root of 729, which gives us 9. Okay, and with that, we can put the value that we found into our dx by dt. Okay, so instead of dx, dv by dx, we have to write dx by dt. So we have to write in its reciprocal 1 over 3x squared, and the x we just found to be 9. So let's just put the 9 in, and then times with the dv by dt given. And because this is the rate of change in with the rate of change of size, so the unit must be cm per second. So with that, we just simplify this. We have 2 over 81 times 3, so 243 cm per second. That's it. We just found the rate of change of the side. Okay, now next, part B. Part B, we have a spherical balloon. Okay, the spherical balloon experience a constant rate of increase of 6 cm squared per second. Okay, now by looking at this, we know that the one given here is actually the rate of change of dA by dt, the rate of change in the surface area. Over here, it never mentioned, just say experiences a constant rate of increase. Increase in terms of what? It never mentioned. However, by the unit, we know that it is area. So let's write it in symbol. dA by dt is 6 cm squared per second. So at the instant when the radius is 5, so when r equals to 5, we have to find the rate of change of the radius. So part 1, we are looking for dr by dt. So dr by dt, we split it into 2 parts, and then we chain together by the quantity that we have, which is dA by dt. So chain together by dA. So we have dA by dt. The thing is, we do not have dr by dA. So we have to think of the equation that relate the A and R. So since A is the total surface area of the sphere, so the area can be written as 4 pi r squared. So dA by dr will be 8 pi r. So we can put this in our dr by dt. But instead of dA by dr, we want dr by dA. So write in its reciprocal. So 8 pi, r is given, that is 5. So times with dA by dt, which is 6. Now radius is length, so the change in terms of the radius, so cm per second. Let's simplify. So we have 3/20 pi cm per second. That is the rate of change in radius. So we found it. Part 2. So part 2, we need to find the rate of increase of volume of the sphere. So dV by dt. So again, we use the chain rule. And now what should we use to chain together? Shall we use dA by dt? But how, if I put dA by dt, but what is the relationship between the V and the A? I do not have a direct relation or equation that relate the V and the A. So I have to continue to split this one. So I split the dV by dA and I chain them together using the radius. So that's it. We can do like this. And by the way, dA, all right, dr per dA times dA by dt is actually dr by dt, which already found in part 1. So we can replace that with this, dV by dr, dr by dt. So we just need to write the equation that relate the V and R. So V equals to 4/3 pi r cubed. Therefore, differentiate the V with respect with R. We will have 4 pi r squared. And let's just put this one in here. So dV by dr, we can use that directly. That is 4 pi, the r is 5. And then times with dr by dt, which is 3/20 pi. Okay, this is the volume, so cm cubed per second. And let's simplify. So instead of 5 squared, we can write 5 times 5. So that the 5/20 pi can be simplified with this. So we're left with 15 cm cubed per second. So we found the answer for B part 2. Okay, now let's move on with part C. Now for part C, the following diagram shows a container in the shape of cone. Given its height is equal to its base radius. So we have the base radius. Let's call it big R. And then the height, because according to the question, all right, it says that it is in the equal length of the radius. So this is also big R. So let's just mark this as the R. It doesn't look like they are equal in length, but doesn't matter. The information given is such a way, so we just take it. All right, the diagram is just an illustration. It is not drawn to the correct scale, okay? And then the water is poured into the container at the rate of 80 cm cubed per second. That means we have the dV by dt equals to 80 cm cubed per second. The volume of water in the container is, so we have this. V is given 1/3 of pi x cubed when the depth of the water is x, which means for this part, if this is x, the depth is x, and then the radius will be x as well. Why? According to the concept of similarity, we have this similar triangle here. All right, so we can compare in this way, the base radius to the height of the cone R. Okay, it will be the radius of the water over the depth, the height of the water. So we simplified this and we notice that actually the radius of the water surface is equivalent to x. So if this is x, this one must be x as well. Okay, all right, now once we get that cleared, So we have to find, we have to find, calculate at the instant when the depth of water is 10 cm. That means when x equals to 10, this is part C, okay, C part 1, when x equals to 10, we have to find the rate of increase of the depth of the water. So we are looking for dx by dt. So dx by dt. So we split this into two parts, and then we chain them together with the rate of change that we have. And the rate of change that we have is in terms of volume, so we chain these two together by the dv. And next, we have to think how to find the equation that relate the v and the x, which is given here. We have v equals to 1/3 of pi x cubed, and therefore differentiate the v with respect of x, we will have a pi x squared. So let's put this one in here. Instead of dv by dx, we have to write dx by dv. So 1/pi x squared. The x is 10, so let's just put the 10 in. And then the dv by dt is 80. So this is the rate of change in terms of depth. So it's cm per second. Okay, so we simplify 80 over 100. So we have 4/5 pi at the bottom, cm per second. So this is the rate of change in terms of the rate of change in depth. Okay, now next, let's move on. This is part 1. And then part 2, we have to find the rate of change, the rate of increase of the horizontal surface of the water. So we are looking for the change in terms of this. Okay, so part 2, the rate of change in terms of the surface area of water. So dA by dt. So we got to split these two, and then we chain them with x. Okay, change them with x because I can write the relationship between a and x. If I chain using the v, then I have to continue to split this one more time, just like part B. So we go straight to the dx. Okay, we have to choose the one where we can write the equation that link that two variable. So in this case, we can find a. The area of the surface of water is written as a equals to pi x squared. Okay, by right it's r, the radius, but we already know the radius is the same as the x, so pi x squared, we can just use that directly. So dA by dx, we will have 2 pi x. So let's put this one in our equation here. So dA by dx is 2 pi, and the x is 10. And the dx by dt we have found in part 1, 4/5 pi. So this is the rate of change in terms of the area. So the unit will be cm squared per second. So we simplify. So 5 pi divided by 5 on both sides, up and down. So we're left with 2 here. So 2 times 2 times 4, 16. So we have 16 cm squared per second. Okay, that's it for question number 31.